4C, residuals and limitations on linear regression equations. Okay, so let's get into residuals and some limitations that we have. And we already spoke a little bit about limitations of the linear regression equation in that we can predict within the range of the data that we have, but predicting beyond is not, it's never guaranteed anywhere we do it, but it is not really just to do so. If you remember, we were talking about the time traveled versus distance traveled, and we created the scatter plot for that, and we said, hey, as the time increases, so does the distance. But then we pointed out that if we go beyond the amount of time, the times listed, there's really no guarantee that it's going to follow that trend. There may be something that occurs after that time that changes things entirely. And times less than that may not be accurately predicted. So basically, when we have a linear regression equation, it's a good predictor in its range. But once you get outside of its range, you know, all bets are off because you don't know what happens outside there. So that's just a limitation that we deal with. And there's the realization that if you have a poor correlation, meaning a weak correlation, that your linear regression equation is not going to create a good predictor of what's going to happen. Remember, I said that the slope of our linear regression equation was very dependent on the correlation. And if you have a correlation of 0, that's going to give you a slope of 0, which means no matter what x value you have, you're going to predict the exact same y value, which obviously is just a poor predictor. So just keep those in mind as some limitations of a linear regression equation. Now I want to get into residuals. Well, what exactly is a residual? Well, the best thing I can do for that is draw a plot. So let's say I have these data values, and I go and I come up with the best fit line, the trend line, the linear regression equation, the least squares regression line, any of those terms we want to use for it. And so I create this line that goes through there that will predict these values. Now we see that this line does not really touch any of these data points. So if I use this to predict what happens at a certain x value, I'm going to be wrong. So if I draw lines, little arrows coming from this prediction line to the actual outputs at those x values, there's a distance between this line and each of those data values or data points. That distance, we can call them d, so we could have d sub 1, d sub 2, d sub 3, d sub 4, d sub 5, d sub 6, d sub 7, d sub 8, right? So, or d sub I, where I is just a number to fill in, so we got our first, second, third, fourth, fifth. Those distances are called residuals. It's a residual. And a residual is the difference between the actual data value and the predicted value. So that's equal to y minus y hat. So the actual data value output versus what we predicted to have happen. Remember, this least squares regression equation is basically the average line. So this is kind of the deviation, like when we were dealing with standard deviations with single variable data, that would be the deviation x minus x bar, the data value minus the mean or the average of those. Now we've got y minus y hat, the actual value minus the average or predicted value for that. So those are our residuals. The whole purpose of a least squares regression line is to minimize those residuals or the cumulative effect of those residuals. We're trying to find the line that minimizes those. So that's why we do that. Well, what do these residuals tell us and how do we find them? So let's go to some data, and this data is going to look familiar. So we've got x and y, 11 and 20, 8 and 21, 16 and 12, 15 and 16, 7 and 23. Right, so we should recognize these before, we've seen them before. And when we had these data values, we came out with a least squares regression line of y is equal to negative 1.04 x plus 30.25. So that's our predictor. Don't forget to put that hat over there, right? This is going to predict what's going to happen with our y values, what our output's going to be. And then we even went further and we said, hey, let's find those differences. And so here, we're going to call those D, the residual, which is, remember, that's y minus y hat, not y bar, y hat. So D, our residual. So we go through this, well actually, before I do that, let's find those y hats, right? Got a little carried away. So, y hat. So we plug 11 into this equation, and we get 18.82. Plug 8 into the equation, we get 21.94. 6 into this equation gives us 13.62. Plugging 15 in gives us 14.66. And plugging 7 in gives us 22.98. So we have all of our predicted values, and we see there's a difference between the actual and the predicted. So now we're going to find those residuals, D, which that's y minus y hat. So we're going to take 20 minus 18.82, 1.18. 21 minus 20.94, negative 0.94. 12 minus 13.62, negative 1.62. 16 minus 14.66, 1.34. And 23 minus 22.98, 0.02. So those are our residuals. And we can see they're much smaller than the actual values. But that's how far off our predictor was from the actual real-world values. Obviously, if we have a linear regression equation, if we have a set of data that has a strong correlation, then these residuals will be smaller. If we have a set of data points that have a weak correlation, these residuals will be bigger. It also depends what range we're in too, what size of numbers you're dealing with, how big or small. But the correlation coefficient is really what's going to dictate how big or how small those residuals are. So why do we care about these residuals? What do they do for us? It's like, yeah, they look nice. We found residuals. Great. Well, what are they going to do for us? What we're going to do is we're going to use them to find out a little bit about our regression equation and about the correlation that we have. So I want to create a residual plot. A residual plot is just a specialized scatter plot. It means instead of plotting x and y, we're going to plot x and d, our residuals. So we're going to create our scatter plot. We're going to have a y-axis. Now what changes with this is, notice that d can be positive or negative. So basically our residual plot is going to be a scatter plot that kind of is a sideways t. Where here we have 0, and we're going to say here are our residuals. Okay, so we've got a residual, and we've got 0 here, and we're going to go up to 1.34, down to negative 1.62, so we're going to make sure we cover those ranges. So how about 0.5, 1.0, 1.5, 2.0, and negative 0.5, negative 1.0, negative 1.5, negative 2.0, just to make sure that we can fit it all in. And we need to, our x values are ranging from 6 through 15, so we're going to need to cover that. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So now we've covered all of our possible x values, and it's just a matter of plotting our residuals versus our x values. So when x is equal to 11, we have 1.18. At 11, 1.18. What's right about there? At 8, negative 0.94. 8, 0.9, negative 0.94. 6, negative 1.62. 6, negative 1.62. At 15, 1.34. 15, 1.34. And at 7, 0.02. 7, 0.02. So somewhere around here. Really low. Okay? So this is my residual plot. Now we have very few data points, but we can see here that the data is kind of spread on both sides. This one's a little sketchy, but we do see that this is low, and then that one's high, and then that one's low, and then that's high, and that's high. So we kind of wonder a little bit about it, but it's not too bad. But as I said, we're dealing with only a small number of data points in this. And just make sure we've got that. So 11, 1.18. 8, negative 0.94. 6, negative 1.62. 15, 1.34. 7, 0.02. And make sure we don't have any negatives in the wrong spots or anything, so we're good. But that's our residual plot. Well, what's the advantage of having a residual plot? Well, this residual plot kind of zooms in on everything. Notice we've got these big numbers there. The residuals are on either side of 0, and they're usually a much smaller value, which allows us to do a comparison and say, hey, does it look like this is linear, or is it possibly a nonlinear correlation? Is my equation correct? If it is, then I should get a nice balance on both sides of the line. This one, as I said, I know my equation's correct. It's really hard to tell with only 5 data points. If we had done more data points, we would see that it is more balanced. But that's what we're looking at for a residual plot. Now let me show you some of the things that we can tell from a residual plot. So let me get this stuff out of the way. And we'll look at what can you tell from a residual plot. if you have a residual plot, I'm just going to label that as X and label this as D. I'm not going to put any numbers in because we're looking in general now. So if I have a residual plot and it looks like this. If I have a residual plot that looks like this and I see all of my residuals are high or all of my residuals are low, they're all off to one side of the x-axis or of 0. That tells me that my y-intercept is wrong. Because everything shifted by a certain amount. So my y-intercept, my base point, must be off. So that's what a residual plot will tell me. If I have a residual plot that looks like this, it's centered about the x-axis, but it's slanted. That tells me that my slope is wrong. On my regression equation, my slope is wrong. I'm centered nicely, which means that my y-intercept's okay, but my slope is off. Something like this tells me that both my slope and my y-intercept are off. Slope and intercept are wrong. M and B are both wrong because I'm shifted and I'm at an angle. Something like that tells me I've got a good predictor. That's exactly what I'm looking for. I am looking to see a nice balance above and below. I'm not looking to see any patterning in it. I just see that it's a scatter above and below. That tells me I've got a good predictor. If I see something like this happening, notice that there's this oscillation in this curve that's going on. That tells me that the data is nonlinear. I may have a pretty good predictor, a pretty good linear predictor, but my data is not linear. Basically, my data might have looked something like this. So you see something like that and you go, well, that looks pretty linear. But when you draw a least squares regression line through it, you see that it tends low, and then it tends high, and then it tends low, and then it tends high, and it's actually oscillating. And by coming in, so I'm going to put this as nonlinear. So it's kind of zooming in and shows me, that was nonlinear data. I could get a better predictor if I used a nonlinear regression equation as opposed to dealing with linear. So that's the advantage of doing a residual plot, is that we can get a kind of a zoomed in look at it and see what's really happening. So we can tell whether our slope is wrong in our predicting equation, whether our intercept is wrong, if both the slope and the intercept are wrong, if it's not really based on linear data, or if everything looks good because we have a nice even smattering of data or residuals above and below the x-axis. The power of doing a residual plot. Doesn't take a lot of effort to do it, but it can really show us even clearer what's going on with our data.